Well, first of all, I'm a professional astronomer, so I have the benefit of access to all of the information from our great new telescopes, both in space. Everybody knows about Hubble Space Telescope, but there's a dozen major telescopes in space that are giving us information about wavelengths we can't see because the atmosphere doesn't transmit them. Very high energy radiation, intermediate energy, X-rays, ultraviolet, lower energy than visible light, infrared. And we've learned that the universe is nothing like anybody could ever have imagined without this scientific information. Everything that we see, all the stars in all the galaxies, is half of 1% of what's actually out there. The universe is almost entirely invisible. The invisible stuff is not known. We don't know what the dark matter is, that's most of the mass in the universe, and we don't know what the dark energy is, that's what's making the universe expand faster and faster. But we know enough about how they work that we actually can make very detailed predictions about the past, all the way back to the Big Bang, and even into the future. And to the extent that we can test the predictions, the tests are coming back with incredible accuracy. Predictions that were made in very great detail by me and other astronomers based on this new theory are essentially exactly correct. As far as we can tell, there are no discrepancies at all. So even though we don't really know why the universe is the way it is or what the main components are, we know enough about them that we have confidence that we've got at least part of the story right. Of course, we desperately want to know what the stuff is, and we may actually find out a lot in the next decade or so. There's good reason to think so. So the bottom line is the universe is more surprising than anyone could ever have imagined. You know, there have been thousands of speculations and theories. Nobody, until recently, when we began to get the relevant information, nobody came close. It's different from what anybody had ever imagined, and yet we understand it to a far greater extent than most people realize, in that we can actually predict the results of observations that we haven't made yet, and then when the observations are made, the predictions are confirmed in microscopic detail. So, I mean, that has got to impress people. It certainly impresses the worldwide astronomy community. Well, the term dark matter was coined by actually a Bosnian, I think, astronomer named Fritz Zwicky in 1933 in an article published in German, and he called it Dunkle Materie, which is just dark matter. And the trouble with the word dark is that it implies that it's black, that is, it absorbs light. But in fact, it doesn't do anything of the sort. It's transparent. Dark to an astronomer means non-luminous. You know, astronomers are used to looking at things that are bright, stars, galaxies. So something that's dark doesn't mean that it's absorbing light, it just means that it's not emitting light. Now, as to what dark matter is, the most popular idea, the one that people are spending hundreds of millions of dollars, literally, to test, and that people are hoping to manufacture at the Large Hadron Collider, is an idea that I first proposed back in 1982 in an article that was published that year. We actually wrote it in the summer of 1981. It was by the late Heinz Pagels and me. And the idea is that the dark matter is associated with a new level of physics beyond what we currently know, called supersymmetry. String theory is actually superstring theory, and it's entirely based on supersymmetry. So if supersymmetry isn't right, forget all of string theory. It's totally based on supersymmetry. On the other hand, if string theory is right, then supersymmetry is right. Supersymmetry says that for every particle that we know, every fundamental particle, the quarks, the leptons like the electron, the force particles like the photon, for every one of those particles, there's a partner particle that hasn't been discovered yet because it's too massive. We haven't had enough energy at our accelerators to make it yet. But in the early universe, there was plenty of energy. And so the early universe should have been filled with these partner particles. Now, as the universe expands, it cools off, the energy drops. The partner particles will decay into ordinary particles. But in most versions of supersymmetry, the lightest of the partner particles cannot decay. The ordinary particles can carry off energy, but they can't carry off something that we call a quantum number that's associated with supersymmetry. So the supersymmetric partners decay into ultimately the lightest partner and ordinary particles that we're familiar with. But the lightest partners are stuck. And as we pointed out back in 1982, if that's not the dark matter, then there's a real problem for the theory, because the universe is going to be full of this stuff. And it should be quite massive. So supersymmetry is a very attractive idea. That's one of the reasons the string theory's been worked out in such detail. So I think many of us hope that, in fact, this story that I just told you is the correct story. It also means that the supersymmetric particles, like the dark matter particle, should be detectable. They interact with the ordinary particles that we know. The reason that the dark matter particle is transparent is simply that it has no electric charge. Any particle without electric charge interacts with light in a very feeble way. If it has no magnetism, then it interacts with light not at all. So we're familiar with particles like that. The neutrino is a well-known kind of particle that has no interaction with light, and also it doesn't interact with the particles that make up the nucleus via the strong interactions. So neutrinos basically can go right through the Earth, right through the sun. In fact, we scientists have been watching the sun at night through the Earth, on the other side of the Earth, because when it's night, of course, the sun's on the other side of the Earth, by catching the neutrinos that come right through the Earth to, for example, a detector in Japan. And we actually see the sun move across the sky through the Earth routinely. I mean, this is not some new, unusual thing. We've been doing this for decades. So we're very familiar with particles like that, but the neutrinos weigh almost nothing. If there's a particle like the neutrino associated with supersymmetry, but that's quite massive, that could be the dark matter. So that's the best guess about the dark matter. Now, as far as the dark energy, the trouble with the dark energy is that there's no similarly attractive theory like the one I just told you. There are lots and lots of possibilities that people have suggested. There must be 1,000 different suggestions in the literature, and actually many of the suggestions have adjustable parameters. So, in fact, there's an uncountable infinity of different possible stories about the dark energy. And the trouble is that none has really stood out as being attractive so that physicists can love it the way we do supersymmetry. Doesn't mean that any of this is right. Of course, we don't know what the dark matter is until we discover it. It might be supersymmetric, it might be something completely different. With the dark energy, the mystery is even greater. Now, the simplest possibility is the one Einstein first suggested back in 1916. He called it the cosmological constant. If that's what the dark energy is, it's simply a property of empty space. Space has this energy associated with it, and it's a funny kind of energy. That's why we call it dark energy, because it actually makes space repel space. So that the more there is, the faster space grows, and then the more space there, so it leads to a sort of runaway, explosive expansion. And that could be what the dark energy is. If that's the case, it's going to be identical every place in space, and it will not have changed at all as we look back in the early universe. We actually know that at present, in the present-day universe, the best measurements are perfectly consistent with this, at about roughly the 10% level. As we go back to when the universe was half its present age, the measurements are only good at like the 50% level. I mean, yes, it could be that it's just the cosmological constant, but it could also be that the dark energy has changed drastically since then by a factor of 2. And right now the measurements just aren't good enough to tell. There are huge projects underway to do better. There's a project that's led by people at Berkeley called the BOSS project, which stands for Baryon Oscillation Spectral Survey. It's a project where millions of galaxies and in particular quasars, the very brightest galaxies that are quite distant, are having their spectrums taken hundreds at a time, hour after hour, night after night. And that's how you can accumulate literally several million. And then by studying these very carefully, we can make better, more accurate measurements of how the universe changed in the past. There is an even bigger project called the Large Synoptic Survey Telescope, a gigantic telescope being built in Chile. We have to get above the atmosphere to see radiation that doesn't penetrate the atmosphere very well to really do the better measurements in the early universe. And the United States has had several such projects on the drawing boards. I was the senior cosmologist in one National Academy study where we said we were given, I think, 11 different projects to evaluate for big NASA projects to explore the universe. And our first choice was the one to study dark energy. And NASA said, sorry, we can't afford to do anything. And then the entire astronomy community every 10 years does an exercise through the National Academy of Sciences. It's called the Decadal Survey. And they said essentially the same thing. The same mission that we proposed, they said, this is what we should do. And the National Academy has always had the highest recommendations followed. It's never happened that the government hasn't followed at least the prime recommendation. But this time NASA said, nope, we just don't have the money, we're not going to do it. The Europeans went ahead and did it. They are committed, but they're doing a much smaller scale mission. A few months ago, the spy satellite people in the government gave 2 Hubble-sized telescopes that are now apparently military surplus to NASA. They're much bigger than what we were talking about for this mission to study the dark energy. They would allow us to do a fantastic job. The astronomers hope that the Obama administration would never have allowed this to happen if they didn't intend to fund it. So we're hoping that if Obama gets reelected, in fact, we will get our dream. We'll get to do an even better dark energy survey than we had imagined because of getting this very valuable instrument basically handed to us. Turns out the spy agencies are using much bigger telescopes now to look down at the Earth. And so the telescope that they were going to use, we can turn around and look out and get a terrific view. Anyway, so there's lots of projects underway to try to figure out what the dark energy is, and many projects all over the world to try to figure out what the dark matter is. Also in space, a number of the different satellites, and we're trying to make the stuff at the Large Hadron Collider, the most powerful accelerator in the world, in Geneva, Switzerland. Incidentally, there is some very intriguing data. We don't know what to make of it. It could be that we are seeing evidence for the dark matter. There's been dozens of papers just in the last few months. We're seeing something. It's looking very interesting. It's too early to, jump up and down and cheer. But if this pans out, we're seeing the dark matter for the first time. And there's lots of hints that we're about to, as we get more data, as we build more powerful instruments, we're on the threshold of a big discovery. We're talking about what most of the matter in the universe is, the vast majority. And it's not made of any of the stuff that we know about. It's not protons, electrons, and neutrons, or quarks and gluons, or it's none of the things we know. It's something else. That we can be sure of. So discovering what it is could be a kind of key that unlocks all kinds of things. It is, after all, the main form of matter in the entire universe. Well, the first data that was really good, solid data was in that paper by Fritz Zwicky, published in 1933, where he coined the term dark matter, dunkel Materie, because it was published in German. And what he saw was that the galaxies in a nearby cluster of galaxies, where there are dozens of big bright galaxies like the Milky Way, they're moving with respect to each other in all directions with speeds greater than 1,000 kilometers per second. The Earth goes around the Sun at 30 kilometers per second, and that's already pretty fast. Thousands of kilometers per second is enormously fast. Now, he could easily measure how much total mass there was in all the stars in the Coma cluster. That's the name of this cluster of galaxies, because you just look at how bright the light is, and that's a really good estimate. And his estimate is right on. I mean, it was done in 1933, but today we would get essentially the same number. And what he could easily do is to see, is the gravity of the stars enough to hold the galaxies together? And the answer is not by a long shot. It just misses by a couple orders of magnitude. It's not even a factor of 10, it's closer to a factor of 100. It's a huge miss. All the stars that we see are just a tiny fraction of the mass. That's what Fritz Zwicky showed. Now, people looked at other clusters of galaxies. I mean, there are many. They always found the same thing. There are no exceptions. Every cluster of galaxies is held together by enormous amounts of invisible stuff. Later on, people were able to measure the speed of stars going around galaxies. They found the same thing. The speeds are much too high. The galaxies would fly apart if it weren't for some invisible stuff that's holding them together. Every time we've been able to measure gravity on large scales, we kept finding that there's some invisible stuff that must be most of the gravity, most of the attraction. We've been able to measure this now many, many different ways. Satellites going around galaxies, the temperature in the clusters of the hot gas, the bending of light from more distant objects by the gravity of the galaxies or the clusters. We always get the same answer. It's not as if there's any discrepancy. We just know there's enormously more matter there than we can see. But this evidence has been building up. The crucial paper, I think, was written in 1979, or at least was published in 1979. It was by two astronomers, Jay Gallagher and Sandra Faber. Sandy Faber is one of my closest colleagues at the University of California at Santa Cruz. And so I was very impressed that they had weighed all the evidence. There were hundreds of papers, but unfortunately something like half of them were wrong, that were suggesting evidence for dark matter. And they had to really look very carefully at all of the evidence. But once they discarded the questionable papers, the rest were so solid that this totally convinced the astronomy community. And starting around 1980, the textbooks changed. And it was clear that most of the mass in the universe is this mysterious dark matter. And then in 1984, I wrote a paper with George Blumenthal, who's now the chancellor of the University of California at Santa Cruz, Sandy Faber, and Martin Rees. Martin just retired recently as the president of the Royal Society of England, and he's still the Astronomer Royal of England. Our paper was the paper that laid out this so-called cold dark matter theory. And as we developed the theory in the years since then, we've been able to make extremely detailed predictions about how the universe evolved, how the galaxies are distributed, the heat radiation that we receive from the Big Bang itself. And every one of these predictions that has been tested has turned out to be exactly right. Not just close, but as far as we can tell, there are just no discrepancies. And that's why this cold dark matter theory has become essentially the standard modern picture, despite the fact that we really don't know what the particles are that make up the dark matter, and we know even less about the dark energy. We don't know their identity. We know a lot of their properties. We don't know why there's as much dark matter as there is. Why is there so much more dark matter than there is ordinary matter? Why is there more dark energy now than matter? Although that changes as the universe expands. As the universe expands, there's more space. Dark energy is a property of space, perhaps. So that explains why the more the universe expands, the more the dark energy outweighs everything else. In the early universe, the matter was in control, which also is why we have to study so carefully the data from the early universe to measure the dark energy. It gets harder and harder to measure as we go back in time because the matter was playing a more controlling role. Still, the dark energy, if it was there, we can see it. We just have to do very careful measurements. As far as we can tell, the dark energy is completely uniform. But as I say, the tests haven't been very precise yet. As far as the dark matter, well, that's very non-uniform. The dark matter is densest in the centers of galaxies, less and less dense as you go farther away from where we see ordinary matter, but it's never non-existent. There's always some. It's just that there's enormously more. There's 1,000,000 times as much dark matter at our distance from the center of the galaxy than there is out in the middle of empty regions of space. So the differences are huge. If the dark matter is the sort of particle I told you about, millions of them went through you as I said that, and me. And it had no effect on us at all. Just like the neutrinos going through the Earth. You need super sensitive detectors to detect the stuff. And in fact, the most sensitive detectors still haven't detected it. But we've learned some great tricks, my experimental colleagues, and we can now make detectors 10 times as sensitive as the best detectors we have over the next 2 years. And there's no question, whoever discovers what this stuff is going to get the Nobel Prize. This is one of the great discoveries of science. So there's a huge race. There are numerous experiments all over the world. I just got back from China, and they're digging a tunnel 2.5 kilometers below the surface as part of the process of building a dam in the mountains. This isn't the Three Gorges Dam, it's another dam in the mountains. And somehow the scientists persuaded the government to make a special tunnel just for experiments. This will be the deepest, easily accessible laboratory in the world. You'll be able to drive trucks into this thing. There's a similar setup in Italy called the Gran Sasso Laboratory, but that's only 1.5 kilometers below the surface, in the middle of a mountain. They tunneled right through it for a road tunnel to go east from Rome. And so at the right spot, you slow down and suddenly make a turn, and then there's a giant door, and you put in the right code, and it opens, and it's enormous. Well, there's going to be a similar story in China, and they're racing to build a detector that'll be the most sensitive in the world. It's the deepest location. You want to be really deep to protect the experiment from cosmic rays, which are just noise, not what you're interested in. So, so all of this is happening everywhere. Of course, we have an experiment in the United States. There are many experiments in Europe, Japan, etc. And mainly, the big news is that people have now discovered how to make these experiments much more sensitive very quickly. And they're now getting into the interesting zone. You know, up until now, they haven't actually had enough sensitivity to detect the stuff that, you know, I and others have thought were likely dark matter candidates. But in the next few years, we'd better detect it, or else those theories are going to get ruled out. There was an article by Penrose and an Indian, I guess, astrophysicist, which made some claims about data from the heat radiation of the Big Bang, and those claims were wrong, and it was very quickly shot down. Those claims had to do with how the Big Bang started, and on that there's a lot of controversy because there's a limit to how much we know yet. But the evidence in favor of the Big Bang is so overwhelming that I can't think of any astronomer who's active in the world, who, you know, for whom this is a relevant issue, that doesn't assume that the Big Bang happened. There were a small number who were trying to come up with any, you know, increasingly weird story to, you know, explain the evidence for the Big Bang. Fred Hoyle was a famous example, and his collaborators. Jayant Narlikar in India is the last of Hoyle's collaborators who's still alive. And he writes popular textbooks about astronomy in which he discusses the Big Bang. And then, you know, he puts in a chapter where he says, now, here are some questions. But the evidence is really overwhelming. Even Narlikar has to admit that the only game in town is the Big Bang. I mean, the first discovery that really established that the Big Bang happened was the discovery of the heat radiation of the Big Bang in 1965. And that's now been confirmed in fantastic detail with the new satellites. There's going to be a lot more data released early next year, early 2013, from the Planck satellite, the European satellite that's even more sensitive than the best American satellite, which is called WMAP. But the preliminary reports are that they're perfectly consistent. It's just going to go a little further. Well, this whole theory I was telling you about, the dark matter theory, assumes the Big Bang. All of these detailed predictions are, if you like, confirmation of the basic story of the Big Bang. Incidentally, it would be absolutely a cinch to rule out the Big Bang. There are any number of observations which, if we saw even one like that, it would mean the Big Bang has to be wrong. No one has ever made such an observation. Well, my wife, Nancy Abrams, and I have written 2 books that address that question. And we don't talk exclusively about things like dark matter and dark energy, stuff I'm doing research on, but more about the new picture of the universe that we get from all of this evidence, and also evidence from particle accelerators and other information about how the universe works on small scales as well as big scales. So one of the surprising things that we now have learned is that we humans are exactly in the middle of all possible sizes. We feel very small compared to the galaxy or the universe, but we're very big compared to atoms or the fundamental particles. And in fact, we're in the middle, and intelligent creatures are all going to be roughly our size. They can't be much bigger, they can't be much smaller, for reasons having to do with physics. So that is one way in which we're central. It's a surprising way. It's not that we're in the middle of the universe in a geographic sense. That doesn't even have any meaning. But it is true that we're in the middle of the observable universe. And the universe is actually very homogeneous on large scales. So so we know a lot about, you know, what the universe is like. As we look out in space, though, we have to understand that we're looking back in time, because the data we get from distant galaxies is data that left them when they were very young. So we can see the whole history of the universe, but of course the part that's oldest is distant, and the older, the more distant. But that's how we fit into the universe. Now, we're also, we now realize, made of the rarest stuff in the universe. The universe is mostly dark energy and dark matter. Most of the atoms are invisible. They're out in between the galaxies. They're not stars. They're not lit up by stars. Most of the atoms in our galaxy are hydrogen and helium. That's what most of the universe is made of, the 2 elements that came out of the Big Bang. But we are made of carbon and oxygen and nitrogen and iron and heavy elements that can only be made in stars. And then at the ends of the lives of the stars, those elements come out as stardust. And so we are stardust. And stardust is the rarest stuff in the universe. I mentioned neutrinos earlier, and we know how much total energy and mass is associated with the neutrinos. Stardust is even less than that. So it is extremely rare. It's 1/100 of the universe. But that's what we and that's what Earth are made of. So another thing we learned is that the natural assumption is that the universe is like what's around us, Earth. Well, it's not. It's about as different as could be. We also have learned that our planetary system is quite unusual. We now have data on several thousand planetary systems. We've never seen anything like ours. We haven't found another planet like Earth. We've found a few planets that have the mass of Earth, but one that was recently discovered is so close to its star that it's practically molten. There's something very special about how our planetary system, the solar system, evolved. And the more we learn about it and about Earth with its big moon, the more special our situation appears. Ultimately, we may discover some more systems that are like ours, but the fact that we've now got data on thousands and we haven't seen anything remotely like ours is beginning to tell us something. So we're special in that sense. We're living in a very special moment on many different size scales. We're living at the time period where the universe is switching over from slowing down to speeding up. We're living at the middle of the lifetime of our solar system. The sun and the planets formed about 4.5 billion years ago. In about 5 to 6 billion years, the sun will turn into a red giant star and it will swallow the inner planets. And Earth will be burned to a crisp and then dissolved. Life on Earth began very quickly after Earth formed. After the Earth had settled down and the bombardment had slowed down, life already formed. So that's in the first billion years of Earth. But it was just single-celled creatures for billions of years. Then, about 500 million years ago, complex life started as the atmosphere became similar to our current atmosphere with about 20% oxygen produced instantly by the microbes. And the oxygen allowed large creatures to get energy. And so you start to get all the different types of life. Now, Earth is steadily warming as the sun, like any star of its type, gets hotter as it gets older. And in a few 100 million years, the Earth will become uncomfortably hot. This is not the global climate change issue. Humans are causing a tremendous change in the climate because we're pumping carbon dioxide into the atmosphere at a very rapid rate. That, in principle, we could control. We can stop it, slow it down, prevent this from getting worse. But on a scale of hundreds of millions of years, incidentally, humans have only been around for a few million years, and people like us probably for 50 to 100,000 years, Homo sapiens sapiens. But on a time scale of hundreds of millions of years, either Earth is going to get uncomfortably hot, and on a time scale of about 500 million years, probably too hot for any kind of life except microbes to survive. All the water will be evaporated, and then the hydrogen will be permanently lost at the top of the atmosphere. And so Earth would turn into a dune-type planet, like the science fiction books. However, our descendants, probably not even our very distant descendants, could probably take care of this problem by simply moving Earth a little further away from the sun. My colleagues in the astronomy community have written learned papers on this. All we have to do is modify the orbit of a large comet so that it can steal energy from Jupiter, which is very massive and has lots of energy, and then deliver a little energy to the Earth to make it move a little bit further away from the sun. Roughly every 100,000 years, that would have to be done. And of course, it has to be done very carefully because a large comet, if it actually hit the Earth, would be catastrophic. But I mean, technically, we can't do this sort of thing. It's sort of macro engineering on a scale of the entire solar system. But in 1,000 or a few thousand years with the development of technology, there's little doubt that this would be quite easily doable. at the stage where we can start to explore other planetary systems, it should be easy enough to modify our own planetary system. So that would keep Earth pleasantly livable for billions of years. But anyway, we're living at a very special time when in the middle of the best period for complex life on Earth. Started 500 million years ago, it'll go a few hundred more million years. We're living at a very special time for life on the planet because there's a species that's undergone exponential expansion in its use of resources, and it's basically disrupting the planet. And that's us. We're causing extinction at a faster rate than anything that's happened in 65 million years. We are changing the climate, and if we keep going, then the effect is going to be really quite catastrophic. By the end of the century, if we keep going at the present rate, all the temperate forests are going to die. The climate zones are going to shift northward, and of course fauna can move, but flora die. And it will be a long time before the forests are replaced, especially if the climate keeps changing. There will be many other drastic changes in the Earth. And and incidentally, that's just one of the many consequences of the exponential increase in resource use and other impacts as we humans not just increase our population, but increase exponentially the amount of resources per individual. Not so much in the West. We already are using a lot of resources per individual, but it's starting to stabilize. But now India and China and a lot of the rest of the populous world wants to catch up with us, naturally. But the consequences, unless there's drastic changes in lifestyle, are going to be catastrophic. And so that's a very special time that may only happen once on a planet. And if we can get through that, we humans over the next few decades, an unbelievably long future, billions of years at least, opens up to us. But that's a challenge. And one of the things we astronomers, I think, can bring to this story is the perspective of billions of years, because that's the perspective of the universe. So we naturally take a long-term view. And of course, if you take a long-term view about the Earth, then inevitably you're going to want to bring under control these disruptive forces. Technologically, I'm optimistic. I mean, I think we can figure out, we scientists and engineers and the public, how to deal with these things, except for the distortion, especially of vast sums of money in the hands of people who really don't want to change in the short term. So, for example, the Koch brothers, I think, said they're willing to spend $100 million on this current campaign to preserve coal and oil, which is their business. Other people are, I mean, there's an increasing inequality in the United States in the distribution of wealth, and a substantial part of the super rich have a stake in the status quo, or even, making it more to their liking. So my main pessimism concerns politics. I don't think that we would have a hard time solving these problems, even because of, I mean, the biggest problem in some sense is the inequality between the rich developed countries and the rapidly developing but still rather poor countries like China and India, which after all between them have about 2.5 billion people. That's a little less than half of the entire world population. But if they reach our living standard in America, where we have 300 million people, there 10 times as many people would mean that we would need several Earths, but we only have one. So, but if we want the world to embrace change in resource use, we're going to have to develop it and exemplify it ourselves. So, I mean, it's frustrating because it's fairly easy, I think, to develop better approaches to all the things we're doing badly from a technical point of view. It's the politics that stands in the way. And then the question is, can really rapid transformations in political, social, psychological, ethical outlooks take place on a rapid timescale? And the answer is undoubtedly yes. I mean, we've seen that, for example, in the role of women, or blacks, or gays in the United States. We've seen it worldwide in various transformations that have taken place associated with religious transformations. The rise of Islam was extraordinarily rapid. Christianity, not so. But so there's no question that these kinds of transformations have occurred on all different size scales, on very rapid time scales. And is that possible in the world today? Well, I don't know. On the other hand, we've never been so linked together in the world as we are now with the technology of communications, the internet, etc. So the opportunity for transformation is there. The question is,